Section 1.2, Basis for a Topology. The purpose of a basis is that most of the sets X we're going to be dealing with are going to be infinite sets, and therefore a topology on such a set is going to be usually an infinite collection of subsets of an infinite set. And such a monster can be difficult to work with at times. In fact, it can even be difficult to specify. And so, instead of describing all of the open sets in a topology, oftentimes we will just specify a special sort of sub-collection of the open sets called a basis. And then, to get all of the open sets of the topology, we'll just take unions of those basis elements. So that's the purpose of this definition 1.5. Let X be a set and B a collection of subsets of X. We say B is a basis for a topology on X if the following statements hold. Number 1, for each element X in X, there is a B in the collection B such that X is contained in B. So you see that illustrated here. We have the set X and an element X in there, and by property 1, there must exist some basis element containing X. And property 2, if we have two elements B1 and B2 in the basis, and an element X contained in both of those, as you see pictured on the right here, then there must exist another basis element B3, which both contains the point X and is contained in the intersection of the basis elements B1 and B2. Okay, so in that situation, then, we say the topology T generated by such a collection B is obtained by defining the open sets of T to be the empty set and every set that's equal to union of basis elements. Okay. So let's check that this collection B of all intervals on the real number line with closed left endpoint and that are open at the right endpoint is a basis for a topology on R. This topology is going to be called the lower limit topology. We'll be seeing it again in the future. So we have to check the two properties. For the first one, we just need to note that for any X in our set, which in this case is a set of real numbers, that X is contained in some basis element. And we have a lot to choose from here. We could, for example, do the interval from X up to X plus your favorite positive real number. How about 1? Okay. And that does it. We've shown that every X in R is contained in some basis element. Okay. As for the second property, this time we are supposed to be given a couple of basis elements, say interval from A to B and interval from C to D. In our basis, and we're allowed to assume that X is contained in the intersection of these two basis elements. Well, what does that mean? X being in the interval from A to B means that A is less than or equal to X, which is less than B. And X contained in the interval from C to D means that C is less than or equal to X, which is less than D. And if we put those two together, we get that, in fact, the maximum of A and C is less than or equal to X, and X is less than the minimum of, how about B and D, right? Because X is less than B and less than D, so it's less than the minimum. Well, that gives us what we need, because remember, we're looking for a third basis element which contains X and is contained in the two that were given to us. And also, what do we have? By the inequalities above, X is indeed contained in the interval from maximum of A and C up to minimum of B and D, right? Which, I've got an extra space there somehow, which is a subset of interval from A to B intersect interval from C to D as desired. So perhaps we can illustrate what we've done here. Let me start with a real number line. And we were given an x, which was contained on the one hand in the interval from A to B, and on the other hand in the interval from C to D, which might be, let's say, from here up to here. And we needed to find an interval containing x and contained in the other two. And for this particular arrangement here, that interval would be the interval from C to B. Because in this situation, the maximum of A and C is C, and the minimum of B and D is B. Okay.